we think that AM is really exciting for space because it gives the opportunity to build parts that are much, much lower in mass, maybe mass reductions of 75%. And that means that these parts can be multifunctional and we can make a really real difference to the volume of payload, the mass of payload, and the size of spaceflight hardware.
We know that the versatility of additive manufacturing, 3D printing, has caused some issues when it comes to part inspection. Again, what's the importance, certainly within a space context, of making sure these parts don't fail?
So the main thing with implementing a technology like AM for aerospace and spaceflight is proving that the parts that you're going to make and you're going to deploy on those missions are going to survive those missions and complete them. And for that, aerospace and space typically uses non-destructive test, which is great. But the downside with AM is that because you can achieve very, very complex shapes, the surface finishes are complex, and it's really driving to much more integration, so much bigger parts. There really aren't that many alternative techniques for NDT that are going to work. Really, X-ray CT is the only technique that is accepted for a non-destructive test for AM parts. But for larger parts and parts made of denser alloys like Inconel, you just can't get the resolution for detecting the sorts of flaws that you might be worried about in an AM part. And that's where our technique comes in, because it can detect flaws in parts that are much larger, and it really doesn't care about the complexity of the part that you present to it.
So companies have started to move away from X-ray CT and start to put in-process imaging in place in terms of part inspection, but there are kind of major pitfalls with that as well, aren't there?
In-process imaging is an effective way of assessing each layer as you build them, but it really doesn't tell you what happens after that layer's been built. And so there might be thermal stresses in the part that really start to accumulate only later in the build that can cause cracking underneath the layer that's being photographed. And then post-process can induce flaws. So the support removal process is often quite brutal, and it's very simple to induce a flaw during support removal or depowdering. And so it's quite important that there's a technique to detect cracks or other flaws that are induced later in the build process.
It is important to have that technique. Nonlinear resonance is set to fulfill that gap. Before we talk about how it's going to fulfill that gap, how does this technology work that Theta Technologies has developed?
So our technique, nonlinear resonance, works by exciting the part with an acoustic signal. And so every mechanical part has a unique acoustic signature, and that's because of the different features of the part all have slightly different resonance frequencies, and they interact in different ways. And so by exciting the part in the right way, we can measure the spectral response of that part. And that spectral response is unique for each part. So even for parts that are nominally identical that are produced by AM, different amounts of support removal might mean that they're physically slightly different, and usually that's designed so that doesn't matter. It doesn't affect the operation of the part, but it does mean that the unique acoustic signature is different. So we can't just rely on the acoustic signature of a part and do spectroscopic comparisons. So nonlinear resonance takes that one step further, and it looks to see how the unique signature changes as we change the excitation. Now, for a good part, a part which doesn't have any flaws in it, you wouldn't expect to see any changes. The acoustic signature of a part is the acoustic signature of the part. But when you excite a part that has a crack in it, say, then at low amplitude of excitation, you get one acoustic signature, but then when you turn the amplitude up, the signature changes, and those changes are the unique signature of a flaw, and they can only come from a flaw within the part. So our nonlinear resonance non-destructive test technique looks just for those signatures of a flaw within the part. So it doesn't care what the shape of the part is, it doesn't care how the different parts are different, although we can measure that. It just looks for the unique signature of a flaw within the part.
So where can this technology fill that gap then that is perhaps left by techniques like X-ray, like in-process imaging? Where is this most beneficial, certainly for space?
So we see this being used in AM parts, perhaps large AM parts, structural elements of a satellite, engine components, thrusters, where those parts might be quite complex. They might have manifolds, pipes, fixings, heat exchanger elements, parts that are very, very complex, but as a solid, they should have a stable but unique acoustic signature. If we see a crack in one of those parts, we'd see that acoustic signature change as we change the excitation, and that would give us the indication that that part might be a flawed part. And we can stop it before there's lots and lots of post-processing that happens later in the stage that costs time and money. And we can also prevent it from failing, detect a part that might fail in service.
So just finally, with effective part inspection, how big can AM be for?
So I think that AM is already seeing a lot of deployment within space and spaceflight, and that is fantastic because it means that we're starting to see the benefits of the technology being deployed. But it's limited by the lack of good NDT. And what I see is that as we're able to prove that our NDT is capable of doing much better quality validation of AM parts, then there may be the opportunity to make parts that are even lower mass, even more optimized, and able to make a real difference to spaceflight hardware.